Hi, my name is Seth Malasgar. I'm a mechanical engineering student at Arizona State University. This semester I've been studying in a class called Advanced Numerical Methods, and one of the things that we've been studying is a method called the Runge-Kutta method. This method is used to solve ordinary differential equations, and in this video I'm going to be talking about a code that I developed using the Runge-Kutta method to solve a system of chaos, or more specifically the Lorentz attractor system. I'm going to be discussing the code, talking about the different things that are in the code and why they're there, and then I'm also going to be talking about chaos as a theory and talk about the different things that can go on with chaos and chaotic systems and non-chaotic systems with the Lorentz attractor models. So let's go ahead and get into that. The first thing to know about the Runge-Kutta method is that it's used to solve ordinary differential equations. These equations that I'm going to be using in this model are shown right here. These are the differential equations that were developed by Edward Lorentz to model weather patterns, and we'll talk about that a little bit later on in the video. The big thing to know about the Runge-Kutta method is that it has different orders. There's second order, third order, fourth order Runge-Kutta methods. And the fourth order is probably the best one to use because it's going to be the most accurate with the least amount of work. However, this code was using a third order Runge-Kutta method, and so that's why you see 1, 2, 3 Q equations along with this next X equation. The Runge-Kutta method is used as a sort of time step approach to solving these differential equations. What happens is if you're given an initial condition, an x and a y, what it's going to do is it's going to use the differential equations. It's going to determine the slope at that first value, which is this Q1 equation. It's going to then step a half step to this Q2 equation, and then it's going to make a full step to the Q3 equation. All three of these steps are going to be averaged in order to be used to determine the function or the output at the next step. As you can see right here, it uses the Q1, Q2, and Q3 equations with the h value being the step size. The big thing to know is that step size is important in these equations, in this model. The step size, as it is bigger, it's going to be less accurate. So the smaller step size you have, the better and more accurate your model is going to be. As stated before, there are multiple orders of Runge-Kutta method. There's the fourth order Runge-Kutta method, there's the third order Runge-Kutta method, and even the second order Runge-Kutta method. With the fourth order Runge-Kutta method, there's a local error to the fifth power with a global error to the fourth power. This Runge-Kutta method that I used has a local error to the fourth power and a global error to the third power. This is important to remember because as time progresses, the further and further you get away from the initial conditions, it means that the further you're going to get from the actual function itself. So it's important to remember that. This can't be used for a huge amount of time. So let's go ahead and talk about what this code is doing and what is in it. We have our initial conditions right here, alpha and beta. These are our time constraints. It has time 0 equals 0 and the end time is 30. M is our total number of data points, while H is calculated for our step size based on M and our time constraints. This gamma, theta, and lambda is used for our Lorentz attractor system. I'll talk a little bit more about those in a little bit. And these are our initial conditions. We have x1, x2, and x3. And these are a set of vectors. This initialize the vectors that we're going to be using in order to store the values that we need with those x1, x2, and x3 values. In the for loop, it runs through from I equals 2 to m1. This starts at I equals 2 because we have our initial condition up here, and it runs to m1 because we have m1 data points. So we want it to run that many times. It first starts with our Q1 equations right here where it calculates Q1. This is equal to xk. It's equal to the function at xk is our Q1 equation. The Q2 equation then is calculated. It's helped with these z equations right here. These calculate this step at a half a step from where we were at. Then those are used in the Q2 equation to then calculate our Q2 equation, which is shown right here, xk plus h times q1 divided by 2. It then goes on to calculate these z equations for Q3, which are used at a full step, not just a half step, but a full step right here for the Q3 equations. This is the full step. So Q1 is the function at that value. Q2 is the function at a half step beyond that value, and Q3 is the function at a full step beyond that value. And then these x equations right here are the next x value that are going to be used. These are the next outputs that are going to be used in the equation. These are all based off of our differential equation that we have given in our governing equations. After that point, these get stored in our vectors right here. You see that x is x1, y is x2, and z is x3. All these values can be stored so that way we can plot them later on. What this code then goes on to do is it calculates a new number of data points and then also calculates the step size based on that. These data points are double the amount of data points minus 1, because what I want to do is I want to determine the error for the data points right here. And so as we see here, the data points are going to determine the step size. If we have double the amount of data points, we have half the step size. And then so we're going to reset our starting values, and we're going to run through the for loop again for those Q equations. So this whole thing runs the exact same way as our first for loop right here. And so the reason that we want to do this twice is because there's not a way for us to determine error for this function. There's not a function for the Lorentz attractor system. We only have our differential equations. After it's gone through and calculated this second for loop, what it does is it has all of those values stored in these x vectors. So we have x2, y2, and z2. And up here, we have x1, y1, and z1. The only difference between these is the step size. And so it's going to use the same differential equations, the same method. And so the way that we're determining the errors, we're taking the x2 values or the x1 values and we're subtracting x2 values. We can't, because there are double the amount of steps or double the amount of data points, we can't just compare one by one. We can't compare the first one of x1 to the first one of x2, second one of x1 to the second one of x2, third one of x1 to the third one of x2, so on and so forth. What we want to do is compare the first x1 to the first x2, but then we want to compare the second x1 with the third x2, because those are the ones that are gonna line up. So we want to compare points that line up, and that's the reason why we have this portion right here, is because that is how we determine what lines up with the next value for x1. So with that, we also calculate a time step. This is solely used for our plots, so that way we can plot our error with time. These are our plots right here. As you can see, we have a three-dimensional plot for x, y, and z with its different labels and titles. We have a two-dimensional plot for x and y with its titles and labels. Two-dimensional plot for x and z, a two-dimensional plot for y and z, and then we have an error plot. So let's go ahead and plot these real quick and see what we got. As you can see in this plot, it starts what looks like to be the same point, but as it progresses, you can see the red and the blue start to slowly diverge from each other. And that is because as time moves on, they start to get further and further apart. This is an example of a non-chaotic system that has a spiral and it converges onto the same point. So this isn't really a great example for Runge Kutta, but you can see between the red and the blue that there's going to be a slight difference as the step size increases or decreases for the model. Now that we know what the Runge Kutta method is and what this code is doing, let's talk a little bit about chaos and the Lorentz attractor system. Edward Lorentz was a meteorologist. He was working on weather forecasting, and he was using a computer program to predict certain results for the weather, and he decided to run a program again to check his values. When he did this, to his surprise, the results were different from what's originally calculated. He looked at his data and found that the only difference was that he had entered a number as 0.506 instead of 0.506127. You see, the computer was running on 6 decimal places while the printer only had 3 decimal places. So when he plugged in 0.506 instead of the 6 decimal places, this tiny little change of writing a number to the 3 instead of the 6 decimal places had caused a great difference in the final prediction. Now what I want you to do is watch this graph and notice that it nearly starts with 2 different points at nearly the exact same point, and just wait and see what it does over time. What Edward Lorenz did is he wrote a talk that was titled with a question: does the flap of a butterfly's wings in Brazil set off a tornado in Texas? What he was talking about was chaos, or more importantly, a sensitivity dependence on initial conditions. What he's talking about here is, even though there's a very, very slight change in initial conditions, it can over time have great significant impacts and lead to something that we couldn't predict at all. You notice right here it starts to diverge a little bit. The blue and the red are going along kind of the same path, but they are not the same, And so as that continues on, they continue to get further and further apart. This is why you see different weather forecasters use models that show different trajectories over time. It has lots of different trajectories because it's hard to predict the exact precise initial conditions for those storms. And so this is why you see that in meteorology. Another example of a chaotic system is one like this double pendulum system, where if you started at initial condition and you take its position at time, say t equals 20, and then you slightly change the initial condition and get the outcome at time t equals 20, you're going to have it at a place that's completely different from the first one. The big thing to know about these chaotic systems is that they're deterministic, meaning they're governed by laws, whether those laws be physical or mathematical. They can have functions to them and we can plot them. However, they're going to have a certain randomness to them. That's kind of the beauty of it, is it looks random, but it is governed by laws. It's not random really at all, other than the fact that the initial conditions change. The last thing that I do with this code here, after it runs through the Runge Kutta method between the 2 different step sizes, is I have a next set of code that does the same thing with the Runge Kutta method, and it changes the theta, gamma, and lambda values. What this does is, if it meets certain criteria right here, as shown in this if statement, that if theta is greater than gamma plus 1 and lambda is greater than theta plus 1 times theta plus lambda plus 1 divided by theta minus lambda minus 1, if these criteria are met, then the system is chaotic. If not, then there is no chaos. And so I ran this code with different values of x1, x2, and x3 for 0, and then you have 0 plus 0.001 to compare, showing how even if there are slightly different initial conditions for a chaotic system, it's going to come out completely different. And so I run through this code again. Let's go ahead and run this and see what we get. What we have here are 2 different systems. We have a chaotic system at the bottom and a non-chaotic system at the top. The non-chaotic system at the top shows a spiral that converges onto a certain point with a very small error. The chaotic system, however, you can see the butterfly look of the attractors. As you can see, they start at about the same point, but then it converges onto the attractor, and it looks as if it's going in infinity. And basically it really is. It's essentially an infinite loop in a confined space, essentially. And then with the error, you can see in the error window for the chaotic system, it's a small error at the beginning, and then it continues to get larger and larger as time progresses. So that's pretty interesting to know. So that's about it for this video. As proven, you can see that chaos and chaotic systems make it hard for us to predict the future too far in advance. Any slight change in initial conditions will lead to a larger change later on in time. One thing I'd like for anyone that's watching this video to do, a challenge for them, is to look for these chaotic systems in their own lives. It could be something like flipping a coin. It could be a pinball machine. It could even be modeling the universe around us. It could be modeling our solar system. It's amazing to see how beautiful chaos can really be.